So I will repeat everything in like 10 seconds, what I just said for the online people. Does it work now? Okay, so sorry for everybody online. You haven't missed anything. I just repeated what we did yesterday. The two algorithms, SARSA and Q-learning. The main thing is that we have this update rule here. And Q-learning is about, well, you have one policy which generates a sample path, and you have another policy which approximates the optimal one. And Raul just asked a question whether there is a heuristic on how to choose this explorative, this exploration policy. And I mean, I'm not a practitioner, that I must say. Yeah, but a reasonable way and something that people suggest is to do still epsilon greedy also for the behavioral, for the exploration policy. And it makes sense to me because you still evaluate the state process somewhere nearly in a nearly optimal trajectory. So you keep updating a lot of the states and actions which really matter to you. Yeah, but you still keep exploring the other ones and try to look for maybe better options every now and then. Yeah, so that's why I think epsilon greedy is okay for that. And you don't need to decrease the epsilon in that situation. You can just keep that constant. All right, we will talk a little bit more about this on policy, off policy business later because it becomes more involved as we proceed. So what's the big issue I would like to address first? It's that assumption that we have finite and small action in state space. Yeah, we saw that in the example yesterday that even in this simple optimal investment problem where we have like 3 time periods, I think I computed the number of state action pairs. This was like 2,500 already. Yeah, and then you need a Monte Carlo estimate for each of these state action pairs. Yeah, and this led to a large data requirement. And you can imagine that if you increase the number of time periods, this explodes very quickly. And because the number of states in the binomial model grows quite large. And state action combinations even more. Yeah, so this quickly becomes infeasible, even in terms of memory requirements, because you need to store a value for each state action pair. So what do we do? Well, what we haven't used yet is that there might be some connection between state action pairs which are close by. Yeah, think of a continuous value function, then you only need to know one value and you have a good estimate for everything around that. And so in other words, if we have a, let's say, continuous state and action space, what do? Well, we try to approximate the value function or the Q function by some parametric class of functions with the parameter being in a finite dimensional subspace, somewhere in RD. And then you have D different parameters which you need to optimize to approximate the entire function. A very simple idea, but that's something that you have to do. You cannot use these tabular methods anymore. What kind of approximating functions can you use? Either linear or nonlinear in the parameter. So linear regression, choose linear combinations of polynomials, radial basis functions, Fourier series, Fourier coefficient, Fourier basis, whatever you like. Yeah, any kind of approximating class of functions, parametric class is okay, to begin with. Or you can do something nonlinear. We all seem to like neural networks nowadays, so you can use a neural network to approximate Q, for example. And then you have your dependence on the parameters, then nonlinear. Yeah, but for the purposes of this talk, it doesn't matter too much what you choose. Yeah, just choose a nice parametric class of functions such that, well, it should be differentiable in the parameter because we will do optimization over the parameter, right? Gradient descent, essentially. And the advantage that we have is instead of having to update all states and actions, we only have to update the parameter to get a good approximation. Yeah, and like this, we can do continuous state and action spaces. We don't have to update. So if the state space is the real line, we would have an uncountable number of states that we have to update using these tabular methods, infeasible. If you approximate everything by polynomials, you have a finite number of parameters to get your approximation. That's the idea. Reduction of complexity. Yeah, that's the upside. Here we can go to more complex situations. The downside is, of course, this also makes convergence analysis much more involved, because things like what we talked about yesterday, the policy improvement result, this only works if you really work with Q or V. If you have an approximation, it's just wrong. Yeah, so there is no guarantee anymore. Yeah, so it will get much more involved. Okay, so let's start really simple and talk a little bit about approximation. So we have some kind of function V defined on some measurable space S. This doesn't have to be the state space. And we would like to approximate that with some function V theta, and we can vary the theta somehow to get as close as possible. And the metric that we use is some kind of L2 distance with respect to some measure mu. Yeah, very standard thing of doing. And what you should think of here in this reinforcement learning or market decision process business is that the function that we try to approximate is the value function of some policy. And mu could be a distribution of some random variable. Let's say the distribution of the state process at some fixed time t. Yeah, and then the integral becomes, of course, an expectation. Yeah, so we try to approximate the squared distance, the squared L2 distance of these functions according to theta. And now, how would you choose, or how would you find theta? Well, the obvious thing to do is gradient descent, right? We start with an initial guess for theta, could be anything, and then you compute the gradient of this loss functional here, and you move in the direction of steepest descent. Yeah, that's gradient descent. So take the current value, the new value is the old value minus step size parameter alpha, and then the gradient of the loss. And this can be computed if we assume everything is nice enough that expectation and gradient here interchange. And you can pull it inside, and then this is what you get. Yeah, one thing to note, which is confusing when you see it for the first time, the gradient here is with respect to the parameter theta. Yeah, it's not the gradient with respect to S. Yeah, because now our variable is theta. This is what we want to optimize. Yeah, S is just distribution. And there you have it. Yeah, this is how you approximate. This is our way of estimating now the value function pi. This is what you do. Of course, life is not so simple because, well, we actually don't know this value function of pi. We still have to figure out a way to get there. But in principle, this is the idea. The first issue we should address, though, is that now in each step, we have to calculate this expectation. And this is expensive, right? In each step, you have to calculate an integral with respect to some distribution. So you need the distribution somehow. We are in reinforcement learning. We maybe don't have the transition kernel. We don't want that. Yeah, this can be and usually is too costly to do. So instead, we're not using the expectation. We just drop it, to get an estimate of that expectation. The Monte Carlo estimate, a very bad Monte Carlo estimate, for example, of that expectation is just use one realization. And that's what we call stochastic gradient descent. Yeah, we use a stochastic realization of that expectation here, of the expectation of that gradient. And this is what we could use. This is the update rule, the new update rule that we could choose. That is gradient descent to stochastic gradient descent. So the intuition behind stochastic gradient descent is, so gradient descent, you move somewhere from a hill in your optimization surface, you try to go the fastest way down somewhere to a valley, to the minimum, from top to bottom, in the most direct way that you can go, steepest descent. In stochastic gradient descent, you don't go straight, but only in mean you go down the direction of steepest descent. We see that immediately. Take the expectation here, and then in the mean, you're going in the right direction. But there's stochasticity, so you, if you draw that as a path, it will not go straight, but it will fluctuate. Just in the mean, it goes in the right direction. So I like to think of it as some kind of a river that flows down from a mountain to the valley. Yeah, it usually does not go straight, but it will make its way somewhere down, not in a direct line, but yeah, move around. Yeah, this is stochastic gradient descent. But on average, when you stand on top of the hill and you look down, it will converge, the river will converge to the valley, to the lowest point, but not just in a straight way. And the nice thing about stochastic gradient descent is that it still works. And the only thing that we need is that, well, what we write down here as our stochastic gradient should be unbiased. So in expectation, it should be this thing here. Then you can get convergence of these things. Of course, you need to ensure that everything is differentiable and it's a nice enough function. So in theta, if it's convex, you would really go down to global minimum. If it's non-convex, you go down to local minimum. All this kind of things.
I have a question. Are we trying to minimize over the class of function v theta or over theta in itself? Because we're looking for a function that minimizes that expectation. And I don't know if theta, like we can find the mapping between theta and that class of function.
I assume that there's a mapping between, so for each theta, you have a v theta.
Okay.
And this functional dependence needs to be nice enough in the sense that you can actually take the gradient. Yeah, maybe it should even be convex so that there is a minimum. Yeah, so our variable is now theta.
Exactly.
Yeah, and we are minimizing theta. Yeah, and the minimum theta is the best approximation then of our target function.
Okay.
Yeah?
Thank you.
Okay, that's what I meant with don't be confused by the S. This is really just the distribution according to which we measure distance. The variable is now theta. Okay, and as I just said, so as long as this estimate here, or our stochastic gradient, the expectation of that is the steepest descent, we are good to go. And this is very nice because in our reinforcement learning applications, we don't know v pi, but it's very easy for us to write down something which in expectation is v pi. Yeah, namely the total discounted rewards. Yeah, so if we replace the v pi by this total discounted reward, if you take the expectation here, you will get v pi. So if you plug that in there, it's still an unbiased estimate of the gradient, and that also converges. And like that, we have a nice update rule where we can approximate this guy with these v theta without actually knowing it. And that's what we need for these approximate methods. Now we have a way to approximate v pi in a very good way to get our estimate without actually knowing it. And this will lead to a new prediction rule. And then you combine prediction with policy improvement and you have your next algorithm. The downside is, we talked about this yesterday, well, if it's really an infinite horizon problem, you will not compute that. Or if it's a finite horizon problem and the number of time steps is large, you also maybe don't want to compute that because you need to sample the entire path. So maybe let's just try to get an estimate for that. And an estimate for that, as we learned yesterday, temporal difference learning, is you take the first reward and then the rest of the series here you approximate by beta times your old estimate for that next state. And here's where you have to be careful, because this is now a biased estimate. This is, if you take the expectation here, this is not the same as this already. Here's where we make an error. And this is where convergence becomes difficult. It depends a lot on how the dependence on theta is. I say a few words on that later. So one way is to use this kind of thing in the stochastic gradient descent. The other one is this here. And if you use this here, it is called
sorry, I missed the point yesterday. So the last temporal difference target, this depends how memory you have in your state process, or I mean, how does it affected by I mean, if you have Markovian kind of dynamics, or you have something with long memory, I mean, in your process.
Everything is Markovian here.
Okay.
Yeah. So for this, you really need just the current state, current action, next state. And then you can write this down. If you want to write down this, you need the entire path. And if it's really an infinite horizon problem, you don't have that. And if it's a finite horizon problem, but with a large horizon, still you need to store a lot. Yeah, so it's not data efficient. Yeah, this here can be done online. Yeah, with each new increment that you compute or simulate, you can update your estimate. That's why people like it. Yeah, mathematicians don't like it. Yeah, because this makes the convergence much more involved. Yeah, but in applications, I think this is almost never done. This is the way to go, or a version of that. Yeah, you can do n steps and then maybe get to lower the bias a little bit. There's a lot of things you can try.
So if I replace v, so the value function, with this last line that you put down here, so can I interpret this approximating this function, or writing this in the expectation and approximating it with v theta as a conditional expectation? Can I understand this as a conditional expectation?
Yeah, in a sense. So what you have here, this guy, is well, we hope that this guy here is close to the v theta, right? Evaluated at x. We know that the v pi satisfies this kind of dynamic programming equation, so you can write this as the conditional expectation. Conditional on your initial state is this random variable s. Yeah, and then you get the first reward, beta times all the rewards you receive after time s1, and this is v in the state s1. And now we just replace the v pi in the state s1 by our estimate. Yeah, so that's the idea where that comes from. And that's exactly what we did yesterday in Sarsa. Just with the Q function, reward, discount, estimate. So this is sometimes also called bootstrapping. Yeah? So instead of computing the series, you try to bootstrap all values bigger than 1, yeah, by plugging in the estimate. Okay, and that's why I have to write here that initially it is distributed according to S. Yeah, that's where the conditional expectation that you asked about comes from. Mm-hmm. Okay, and now we have this update rule for our estimate, and this leads to versions of Sarsa and Q-learning by the same ideas as yesterday. So these are then called semi-gradient because we're not computing the gradient in the gradient descent, but an approximation of that. That's why it's called semi-gradient. And then the update rule looks like this. Yeah, it looks almost the same as the Sarsa that we saw yesterday. It's reward, estimate for the next value. Yeah, so the value in the next state minus current estimate. Now we have to multiply that by the gradient with respect to theta that comes from gradient descent. And we update not the value function, but the parameter of the value or of our estimate. Yeah, gradient descent or stochastic gradient descent with bootstrapping. Yeah, that's also a way of putting it. And Q-learning, you do the same thing, except here you maximize over the choice you have here. This is analogous to what we did yesterday. And now we have two approximate methods, semi-gradient Sarsa, semi-gradient Q-learning, which work also for large uncountable state spaces. And the question you may have now is, does that converge? And this is the slide where I was really most worried about, most afraid of when preparing my part of the mini course. Because as a mathematician here, I feel really uneasy about these results that you will see now. First of all, semigradient Sarsa, yeah, with an approximation which is linear in the parameter. This is the nicest, yeah. And here you can show that it does not diverge. So it will converge, but what it converges to is not optimal in general. What's this? The reason for that? It's because that stochastic gradient descent we have here, we have a biased estimate of where we want to go. Yeah? So it will still converge, but it won't converge to the right thing, yeah? Because we don't write down the right gradient. It converges to something else. You can bound the error, yeah, even in the stochastic gradient descent thing here. It's like 1 over 1 minus beta times the minimum value that you can achieve. So it depends on the discount factor. If the discount factor is large, you have 1 over 1 minus beta, this will be very large. Yeah, so if beta is large, you care much about later values in the reward. Yeah, then of course your estimate is bad. Whereas if beta is small, you have almost 1 over 1. Yeah, and if beta is small, you only care in this series here about the first couple of terms, then this estimate is better. That's the intuition.
So the intuition says that if you add more beta terms, it will go better. So the bias. I mean, if you pay the price of adding more in that expansion somehow.
The intuition is that if in that series you see here only the first couple of terms matter, then it's better.
Sure, but if you have beta that is larger, say, should you add more terms in the expansion to try to reduce the bias?
Yeah.
Would that be a way to control?
That would be a way to make it better. But there are also other methods which can improve on that.
Okay.
Which we'll not get into
sure.
for lack of time.
But from the numerical analysis point of view, we want to understand which are the discretization parameters, so to say, so to try to get better convergence. So playing with the number of terms could eventually make the thing consistent, right?
Yeah. And that's the big business in these kind of methods. Try to come up with something better here, yeah, which is closer to what you want to have while still being data efficient. Yeah? And there are a lot of things you can do. People get very creative, yeah, but that's the thing. Yeah, remove the bias, and maybe so this one you won't want to do because this has a lot of variance potentially. This one you don't want to do because it has a lot of bias. Somewhere in between, this is the sweet spot.
Sorry, just to follow up on that formula. Sometimes when one has a sum of infinite number of terms, one randomizes over the indices in the sums to try to make it unbiased, but still compute, say, a few terms. Do they use that?
Not that I'm aware of, and I'm not sure if it helps because you still have to compute the entire path anyway, right? Up to the last one. So you could reduce variance probably.
But in this generation, for example, in games or things like that, when you have the whole path, for example.
Not that I'm aware of, but
okay,
maybe.
Thank you.
Okay, so convergence. As I said, this really feels unsettling for me, but we will resolve it. Yeah, so Sarsa, linear. Yeah, that's the nicest situation that you can have. If you have linearity in theta, then it means for the gradient descent you have a convex optimization problem. Gradient descent would go to the global minimum. Stochastic gradient descent, because of the bias that we have, will converge, but not to the global minimum, but somewhere in the vicinity. And we have potentially a bound in the error, which may be, which you can try to control in a certain, or try to make small using a proper setup of your algorithm. If you go to the nonlinear case, things get more complicated. Think of a neural network. Even gradient descent or stochastic gradient descent, this will not converge to global minimum. The best thing that you can do is a local minimum. It will converge, but we have this bias in there, so things get much more complicated. There seems to be a counterexample where we actually get divergence, but this is a very artificial one. But nevertheless, this already tells you mathematically this is not so nice. Yeah, for us to prove something. Q-learning.
So when you meant the linear case, you meant also this encompasses polynomial and lot?
Yeah.
Okay.
Yeah. So just linear combination of basis functions. And then in theta, because we're squaring, it becomes a quadratic, and this is nice. Nonlinear means just anything. Okay, Q-learning is much more complicated. There are easy examples where you can see that it diverges. Yeah, so here you have to be very careful. Mathematically, things get very complicated. This does not mean that in practice these things are not used and do not work. Yeah, people still use them. Oftentimes they still do work, but you need to be very careful. Yeah, you have to spend a lot of time on hyperparameter optimization. Yeah, so in general, this is a very complicated business, because imagine a neural network. If you just try to approximate one function, even there you will have to tune your hyperparameters to get good approximations. Here we add on top the control problem. Yeah, so we are optimizing, we are shifting the function that we are trying to approximate. Yeah, we are approximating q pi and we are changing pi. Yeah, with one neural network. Yeah, so the function that we're trying to approximate moves away from us. Yeah, and we have to follow up on that. Yeah, and that makes it even harder to make things work. Yeah, so reinforcement learning is harder than this deep neural network business. Yeah, because of that reason, yeah, it does not get easier. So people say the more PhD students you have, the faster you can get a running algorithm. Okay, here's something, as I said, I'm not a practitioner, but apparently in practice, what one observes is that these on-policy methods, SARSA, they have better convergence properties, which we can kind of see from the discussion. But if the off-policy, so Q-learning converges, it typically finds better policies. Yeah? And looking at this, these statements here, we have reached a point where we can no longer expect to find optimal policies. Yeah, because even in the SARSA linear case, yeah, it doesn't diverge, but we won't approximate the optimal function. And when I first saw this, and this is why I felt uneasy with that slide, because that's unsatisfactory, right? So I do research in stochastic control. The only thing I'm interested in is the optimal control. I don't care about other policies, especially in that situation where I may not be able to judge how good that is. And because I only have the data available, I don't know what the optimal policy is. I cannot judge how far off I am. Yeah, and this doesn't feel good, yeah, as a mathematician. But then came the thought, that doesn't matter. Yeah, so if you think about it, when do you use reinforcement learning? The examples that we had yesterday in the very beginning, we had something like playing games like chess and Go. Yeah, I don't want an optimal strategy. I don't even know if there is one. I just want to be better than everybody else. Yeah, so I have to compare my strategy against benchmarks. As long as I'm better than everyone else, I'm happy. Or if you do optimal investment, we had this hedge fund example yesterday. I don't care for an optimal strategy. Yeah, I just want to do better than the hedge fund is currently doing. Actually, I don't want an optimal strategy because I want to improve the strategy, get a fat bonus, then improve it one more time and get another bonus. Yeah. And
that is the optimal strategy.
Yeah. It's just a different performance criteria. Yeah, exactly. Or look at us as researchers. So I've published a couple of papers on optimal investment. Yeah. Why do I publish more than one paper? It's because, well, we start with simple models, try to find the optimal strategy, and then we get to more complicated models. And none of the optimal strategies that we compute are optimal in practice because our models are wrong. Yeah? So in a sense, we are doing the same thing. It's just that we are lying to ourselves by assuming we have a model and it's optimal. But in practice, when we work with data, when we apply this strategy, it will not be optimal. There's always someone who outperforms us if we do that. Of course, it makes us feel more comfortable because we can say, okay, it doesn't work because the model assumptions are not satisfied. I may have an idea of why I'm not optimal, but it's the same thing. All that we are trying to do is try to find good strategies that work with real life data. And we either do that by doing models and optimal controls, or we do reinforcement learning on the data, and then we compare ourselves to what other people are doing. And I think this is the big here of today's talk. It's not a bad thing that we don't get to an optimum. We just have to shift our way of thinking. I think for us mathematicians, this is much more difficult and harder to realize than people doing computer science because they're closer to data, or the problems that they look at. It's clear that there's no optimum that you can achieve. And so that's my main message for today. I want to say a few extra things on Q-learning. Why is it harder than SARSA? You see that here. Even in the linear case, this may diverge. And there is a reason for that, and it has the nice name, the Deadly Triad. So there are just too many things that we are doing wrong, slightly wrong, but that adds up, and that makes Q-learning harder. The first thing that we do wrong is we don't work with the value function or the Q function. We do function approximation. Error number one. Second thing that we do wrong is bootstrapping. So instead of writing down the total rewards, we use the current reward plus whatever we hope we got right. We have a biased estimate of the target. And the third thing that we do wrong is off-policy learning. And this is a bit harder to understand, but the intuition is kind of, so you're generating your data using one policy, so that's one distribution, but your update is according to a different policy, which uses a different distribution. And if you're doing stochastic gradient descent, the distributions more matters. So you're going one way, but you're trying to optimize in another way. And this leads to, in practice, to the target being much more unstable. It moves around, and this is when divergence happens. We see that if we have divergence in Q-learning, this means that this guy is too wild as we go through our optimization steps. And one of the reasons is that here we use a different policy than we use to generate the data. And this is called the Deadly Triad. And there's a lot of things that people have tried to do, especially in the last 10 years, to overcome these issues. The main thing is making the target more stable in a suitable sense. There are these TD lambda algorithms. Double Q learning is quite interesting. So essentially, you just estimate your Q function twice. Use one for generating, or you switch back and forth between them, and this removes some of the bias that you have in the target. And as I said, there's a lot of things that you can do here. If you're interested in these, check the book by Sutton and Bartow that I mentioned yesterday, the reinforcement learning book. They have a lot to say on that. They also go into everything much more detailed in what I said. And that's it for approximation methods. And now I was hoping to get through this a lot quicker. I actually had another method prepared, policy gradient. I will just skip that because time is pretty much already up. Instead, I will just jump directly to the conclusion. I'm fine doing that because I got the main message across, and that's all I wanted for today anyways. So the second part, which I'm skipping now, it's just another way of doing it. You just go directly on the policy and you do stochastic gradient ascent on the policy. You approximate it with a parameter, and then you try to optimize the parameter because we have an optimization criterion. Why not do stochastic gradient ascent directly? And this leads to so-called policy-based methods, which we won't see. You can also look that up in the book that I mentioned.
If you do that, that should be simpler to analyze.
Yeah, this is a lot simpler because this comes directly from stochastic gradient ascent. Yeah, so you get directly the convergence properties from there. They typically converge to local optima, but you get convergence much easier.
What is a minus? What is a minus in comparison to this?
Sometimes it's not necessarily, so it depends, yeah? So either you're approximating the policy or you're approximating the value function. And depending on your problem, yeah, one of them might be more easy to approximate or more difficult. Depends on the problem itself. And so there's no universally superior approach. It depends on the situation at hand. In terms of convergence analysis, policy gradient methods have clear advantages, but of course, immediately after realizing that it's just stochastic gradient descent, you try to improve that. You use biased estimates, and you end up with the same business, yeah, and you try to be more data efficient and so on. Yeah, so there's also a huge stream of algorithms in that direction. Yeah. But keep in mind, there's more than these value-based methods that we've seen. That's the point I was trying to make. Yeah, depending on the problem, one may be better or the other. Okay, and this somehow concludes what at least the first question that I wanted to address. So if the state space becomes large, we do approximation, convergence gets more complicated, but you can extend these algorithms, and to a certain degree, they give you good policies. Yeah, if you massage the algorithm long enough, if you have found nice enough hyperparameters. And that these things really work, you can see, coming back to the beginning of yesterday from the news articles, yeah, we have reinforcement learning agents that beat every Go player in the world, yeah, easily. Chess has been known for a long time that machine learning algorithms do much better than humans. And we keep getting new results in this direction. So even though mathematically this feels not so comfortable, that we don't have this convergence to optima, or we have to worry about convergence at all, there are still a lot of examples where this produces extremely good results. Yeah. But you have to be very careful about setting up your algorithm. And I think that's also what I like about presenting it in front of all of you is because you are probably the right people to think about this kind of things, because you know stochastic numerics, you know about these are all somehow Monte Carlo based methods, stochastic gradient descent methods. You know the importance between unbiased and biased estimates. You know about the importance of reducing variance. Yeah, so you have all these tools available. Why not try to apply them in reinforcement learning, yeah, and tell the computer science guys how to do it mathematically rigorous, yeah, for example. Yeah, so it's an invitation for you to have a look at these things, because computer science is big on that. Mathematics is still in the early stages, I would say. There are a lot of open questions in there. Have a look at it. Okay, the only thing that I haven't addressed yet is the data problem, but unfortunately, I already took away the main message yesterday. I won't say anything about data because I'm not that kind of person. I do theory, yeah, and I don't work with data. For financial applications, yeah, let's think about the hedge fund again. You have a couple of realizations at most of a price path, yeah, and now you want to train your reinforcement learning agent on that. Forget it, yeah. If you just use these data points that you have available, this makes no sense, yeah. So you need to be able to gather a lot of quality data. You could try a different price path from other prices which are related, add them in, but then your data is wrong, yeah, and then you will get, yeah, garbage in, garbage out. So you need a way of producing a lot of data from very little data. Yeah, you need a good oracle. Yeah, you need a good way of bootstrapping or simulating new data from very little given data. And we have one person who knows how to do that, and that is Blanca. And she will tell you all about that. So Blanca, we need you in 5 minutes because everyone needs a short break after my talk, but we are very much looking forward to hearing from you. Thank you very much.
Thank you very much, dear Christoph, for this really great introduction to reinforcement learning. Are there any questions from the audience right now?
My question is about the optimization process. Like, I don't know if you like investigated why it's may not converge in certain situation, but probably isn't it because we're using like the gradient descent method? Isn't like exploring using other methods maybe a solution for that?
Yeah, so you can of course come up with other ways of trying to get a better function approximation, other algorithms than gradient descent, stochastic gradient descent. Sure, definitely. Yeah. What you should keep in mind is that it should be, it would be good if it is something which you can do online. So whenever you get a new data point in your sample path, you should use it right away to be efficient on your data and not having to simulate too much and then use very little of that. But nothing stops you from choosing something else, of course. If you do stochastic gradient descent, you could vary your initial parameter to get from one local optimum to a better local optimum, and things like that. Yeah, all the things that we know that we do for ordinary function approximation, they potentially help us in reinforcement learning. The better the approximation, the better the result. And the more stable the convergence, the better the reinforcement learning.
Other questions?
Yes, thank you. So I also had some projects where I had a lot of data and where is balance? Nowadays, satellites, for example, can give you millions of data, yes? Or maybe some another software can generate for you data. Where is limit? How to say it's enough? Yeah.
Well, if the algorithm stabilizes, if your policy doesn't change by much, or if you have an estimate for the value, if you see that it stops improving, that's where it's okay to stop.
Yeah, this is what a little bit strange. In my case, for example, it was identify 3 parameters, scalar parameters, but data which I had was 2 million data, 2 million observations.
Mm-hmm.
So somehow something is wrong here. If you to find just one scalar function, you need millions of data.
That's because you don't have a model. Yeah, so you somehow, internally at least, have to estimate the state dynamics, and for that you need a lot of data.
Okay, thank you.
Yeah, my guess. Yeah, of course, it depends always on the concrete situation, but since everything here is potentially model free, you need a lot of data so that your algorithm can learn the dynamics. Otherwise, it produces garbage.
Okay, thank you.
Yeah.
All right, then let's thank Christoph again, and let's restart at 10 o'clock.
Thank you.
Yes.
So can we
No, already. Okay.
Thanks.
Yeah.
I know she's here.
Yeah.
Very helpful.